Hello everyone, my name is Wayne. I'm a current grad student in McMaster University. I'm also a former level designer and project manager in Shanghai Jane Network. Today I'm glad to present my research, Can Deep Learning Predict Programmatic Gaming, which is a study combined with e-health and artificial intelligence. I finished it with my supervisor, Dr. Jack Krett. So let's start with the concept of programmatic gaming. So what is it? Programmatic gaming is used to describe the programmatic use of video games. It may also be known as gaming disorder and video game addiction. And in 2018, the WHO added gaming disorder into its international classification of disease. In 2013, the APA added into the DSM-5 as a mental disorder. So far, there are three techniques to detect programmatic gaming. First, the genetic testing could be used to estimate the probability of developing game addiction. Second, the relationship between game disorder and human brain waves can be analyzed by electroencephalograph. Third, as the mainstream method, gaming addiction could be diagnosed by questionnaires. However, none of these methods could be used effectively in commercial games, so that's why we want to make a prediction model based on game log data. As for the data side, we use the log data from the famous game, A League of Legends, the LOL. We cross data from a database which is free and public. To make the data set be more general, we sampled the same number of players in each rank, from Iron to Challenger. We used time steps to crowd the in-game behavior from April the 1st to August the 19th. The features include the user ID, the game starting time step, and the duration for each game. As for the pre-processing, we first convert game log data into time series data. To do this, we make the user ID as the index and group time into discrete duration measured by hours, which then become columns. After that, we use the weekly gameplay and the time rolling window to label each weekly playtime. The weekly gameplay, WG, is developed by the APA to describe the excessive use of video games. It has 6 levels as shown in this figure. For example, if weekly playtime is less than 7 hours, the green line, it is judged as the level 0, and if the playtime is between 8 hours and 14 hours, that is level 1, and so on to level 4 for more than 40 hours. APA also mentions that serious excessive gaming could be defined by playtime is greater than 30 hours, which is level 5 and level 4 in our model. We next focus on the observation duration, which is very important for machine learning and addiction prediction. If it is too brief, neural networks will lose accuracy on the testing set. If too long, we may miss the best opportunity to warn potential gamers. In our research, we first set a reasonable value range for the period, the lower bound of 7 days and the upper bound of 28 days. This range is then used to extract the duration required for the development of each player's first excessive game behavior. In our algorithm, there are 3 examples as shown in this figure. In the first case, the value is in our range, so it is taken as the duration we want. And in the second case, the value is out of the range, so the upper bound is taken as the duration. In the third case, the first value is less than the lower bound, so we discard it and continue compute the next value. After compute all players' observation duration, we got an average about 14 days, so we finally choose 2 weeks as the final duration. In the modeling experiment, 4 deep neural networks, the RNN, LSTM, BI-LSTM, and the network combined with deep autoencoder and BI-LSTM were tested. We only describe the details of the last model in this presentation. Others could be found on my GitHub mentioned in the paper. We first scaled the input data. DAE was then introduced to relieve the impact of uncertainties of input, such as survey maintenance. DAE also rebuilt the data and generated new patterns for us to analyze. The encoder takes the original input and compressed it into a feature vector, which is then reconstructed by decoder to full dimensionality. The reconstructed data served as input for the stacked by LSTM. Because we are trying to solve a multi-class classification problem, softmax was introduced as the activation function, and finally, we could get the prediction of future playtime. To verify the feasibility of our predictions, we conducted 7 tests, fixing the number of days in advance from 1 day to 7 days to 6, which network has the best performance for each test. So, in this case, the hypothesis of our first experiment is, with a change of the number of days ahead, which could also be realized as the difficulty of prediction, the selection of the best model also changes, and the accuracy and average cross entropy on the testing set are the dependent variables. The independent variable is the number of days in advance for making prediction. We can see the result in this form. The correlation of data decreases with the increase of days ahead. Generally, when predictions are made 1 day ahead, networks only need to predict the playtime on the 7 days, as there is a 6-day overlap between the target week and the observation week. However, such overlap does not exist when predictions are made 7 days ahead, and there is thus no partial correlation among features and labels. In the first 3 tests, by LSTM got the best performance since it works better in correlated data. As for DAE by LSTM model, the accuracy failed to get more than 60% in all tests because a deep autoencoder breaks the correlation when rebuild the data. However, in the last test, the negative effect of DAE was non-existent, and the reconstruct data also obtained new patterns from feature vectors, which further improved the accuracy of by LSTM. In our second experiment, we conducted a quantitative research based on a comparison between our prediction and mainstream game addiction scale, the GAS. On May the 12th this year, we conducted a survey among 26 college students who are also play LOL. We first asked them to fill the 7-item GAS questionnaire. Based on their log data, we then use weekly gameplay to label their actual playtime from May the 5th to May the 11th. We call this the actual weekly gameplay, the AWJ. Finally, we use our prediction model and their log data from April the 28th to May the 4th to predict their playtime, and we call this predicted weekly gameplay, the PWJ, and we choose Fisher's exact test to validate the result. Since we only have 26 subjects, it's a small-scale experiment. We use 2 contingency tables to report the results. In the first table, since p is far less than alpha, which means the weekly gameplay is strongly correlated with the GAS and thus could be used to describe game addiction. And in the second table, p is also less than alpha, which means our model could also be used to predict problematic gaming among college students. In the end, the take-home message of this presentation: first, excessive gaming has a strong correlation with problematic gaming, which is proven by our second experiment. The second, problematic gaming could be predicted among college students by analyzing their game log data based on deep neural network. Third, deep autoencoder may improve the accuracy when predictions are made 7 days ahead. Finally, we want to use movie lines of the Ready One player to end this presentation. We all know that in the age of game AI technology, the virtual world will become more and more real. However, I hope that more research could focus on how to maintain the balance between the virtual world and the reality, because the reality is where we truly belong to. The reality is the only thing that's real. Thanks for listening.